How we doing, guys? So this next video is on Fundamental Applied Maths, Chapter 11C, pages 199, 200, questions 2, 4, 7, 9. This set of exercises is essentially a continuation of some of the questions we've done already. It's just in different forms that they're cropping up. So we're going to have a look at question 2 here. Car turns around a bend on a horizontal road. The bend forms an arc of a circle of radius 24 meters. If the coefficient of friction between the car's tires and the road is 2/3, find the maximum speed with which the car can safely take the bend. And part 2, in wet weather, the maximum speed is 7. Find the coefficient of friction between the tires and the wet road. So let's set up question 1 there. We're going around a bend, and your car going around a bend, if you're looking at it head on, might look like this. Okay, there you are driving your car. Okay, and as you're traveling in a circular path, okay, so that's the front of the car there, if it's not too obvious, your inward force is supplied by friction with the road. So in this question, the inward friction is what supplies your centripetal force. So friction is mu r. So your car, mu is 2/3. So 2/3 of whatever the reacting force is. Now, because you've just got weight acting straight down and you're not on a bend, there's weight acting straight up as your reacting force. Sorry, you're not on a tilt. So 2/3 mg is friction. The centripetal force then, now you're being asked about speed, which is velocity, so we'll use the mv squared over r, and the radius in this question was given as 24 meters. Okay, the radius of the turn. It doesn't have to be a full circular turn. Part of a turn can just have a radius of 24 meters, so if the car is turning from here to here, it's still going through a turn of radius 24, even if it's not doing a full circle. So the question is find the maximum safe speed. So if it needs to engage fully that 2/3 mg, that full amount of friction, then it's at its maximum speed. If it goes any faster, it'll need more friction that it won't have. It won't have that 2/3 mg, so it'll start to skid out to the side, or at least it'll feel like skidding to the side. What the car wants to do is carry on traveling in a straight line, according to Newton's first law. So V is what we want. We know R. So we're saying 2/3. Sorry, I just cancelled m's there. This problem is mass independent. 2/3 of g equals v squared over our radius is 24. Multiply through, that's going to be 48g over 3 is v squared, and v is the square root of 48g over 3, which my calculator's gone. Okay, well look, we'll find the answer to that. I'll leave you guys to do that. Question 4 is the next one we'll have a look at. A car turns around a bend on a horizontal, part 2, excuse me. If in wet weather the maximum speed is 7 meters per second, find the coefficient of friction between the tires and the wet road. So now we're saying we're saying the frictional force again is equal to the centripetal force. It means mu r, mu times mg, has to equal mv squared over r. Same equation that we used up here, except we've got a new coefficient of friction because it's wet. Again, it's a mass independent problem. M's cancel on both sides here, and our maximum velocity, we're told, is 7 meters per second. So if you go any faster than 7 meters per second, you're going to skid out. Radius is still 24, so what's mu? It's going to be 49 over 24 and dividing across by g. Okay, so I got a new calculator here. So 49 divided by 24 is that, divided by 9.8 is that, 2.08. Sorry, 0.208, which I'm sure This calculator won't change it to a fraction for me, but I'm sure that'll change to a tinier fraction. Up here, the square root of 48 times 9.8 equals that, divided by 3 is that, and the square root of that is 12.52 meters per second. Okay, question 4 says a book rests on a horizontal shelf in the back window of a car. Coefficient of friction between the book and the shelf is a half. The driver of the car takes every bend at 6 meters per second. Find to the nearest meter the radius of the tightest horizontal bend which the car can take without the book slipping. So same type of thing you have going on here. You can think of this book as just going around in a circle with a surface on a surface. Okay, so the book is stationary, the surface is what's moving around in a circle. Find the radius, the tightest radius you can go through, where the book doesn't slip. So again, the book has weight mg, so there's a reacting force mg. So the friction, and it's called the limiting friction. Okay, it's just the friction, the maximum friction that this thing will engage before it moves, will be its coefficient of friction, which is a half times the reacting force. So half mg is the inward force, and that's what supplies this book with centripetal force. That's what allows the book to move in a circle while the car also moves in a circle. If that was a marble, it'd roll and the car went around the corner, okay, because the marble won't necessarily stay still due to friction. The book will up to a certain speed, and then it'll get thrown across the car. So we are saying that a half mg, that's the frictional force, is what's supplying our centripetal force, which is mv squared over r. Again, like most of these problems, mass independent. So that's going to be 4.9 equals v squared. V squared is every bend is taken at 6 squared over r. So multiply across r is 36 divided by 4.9 when you rejig that. And 36 divided by 4.9 is 7.34 meters per second. Now, I happen to know because I look at the back of the book, I have a big red mark through it, so I obviously did this question before at some stage and concluded the answer to the book at the back is wrong. And yeah, I think the answer to the back is 6, so 7.34 is the correct answer here. Okay, question 7, I said I'd have a look at next. So, question 7, an aircraft of mass 50 tons describing a horizontal and circular path of radius 4,800 meters. The sine of theta, the angle of bank shown in the diagram, is 5 over 13. L represents the lifting force. Taking g as 10 meters per second, calculate the speed of the plane to the nearest meter per second. Okay, so here's just another example of a circular motion problem, but applied again to a new circumstance. So we've got our plane here. And for those of you who don't know, when air passes over an airplane's wings, you get a force called lift. They're designed to kind of generate this force, and it acts perpendicular to the surface of the plane. Okay, so L for lift there is perpendicular. So here's our plane. Again, I'll do a really poor diagram of a plane. Now, the circle, the path that we're moving in, looks something like this. Okay, so that lift has to be resolved into components inwards and upwards. Okay, so I'm going to redraw that vector diagram over here, or down here maybe. So here's our lift. We've got an upwards component and an inwards component. And we're told that the angle of bank here is theta. That's this angle here. But because that line and this line are parallel, we can say that this angle is theta as well. Okay, that is alternate angles on parallel lines. So we know that sine theta is 5/13 is what we're told. And a quick go of Pythagoras here, 13 squared minus 5 squared will tell us this is our 5, 12, 13 triangle. So if that's L there, this component here is going to be L sine theta, which is 5/13 of the lift. This component here upwards is going to be L cos theta, which is 12/13 of the lift. Okay, so sine theta is 5/13, cos theta is 12/13, adjacent over hypotenuse. And G is 10. So the other force acting here is the airplane's weight, which is 50 tons, which is 50,000. Again, multiplied by G, which is 10 in this case. We're not taking 9.8. So that acts straight down. So our first equation is that the forces up have to equal the forces down. That is, there's still enough upward lift to keep this plane in the air. So our force up is 12/13 of our lift, and our force down is 50 tons is, 50,000 times G is 500,000. So 500,000 newtons is our upwards force. Okay, so that tells us straight away that our lift is 13/12 times 500,000. Forces in have to equal our centripetal force. So our inwards force here, this component of the lift was 5/13 of the lift. That equals our centripetal force, which is mass. Now what are we working with? The speed of the plane is what you want, so that's going to be mv squared over r. So using mv squared over r, we're going to get a mass of 50,000. V is what we're looking for, and the radius of our turn, we're told in the question, is 4,800 meters. Or 4.8 kilometers, but we'll stick with meters, standard unit. So that gives us an expression for the lift is 50,000 v squared multiplied by 13 divided by 48,000 times 5. Okay, so these two expressions are equivalent, and then v squared is our only unknown. So we'll say 13/12, and it's useful to leave this in factorized form. In fact, even that you could have left as 50,000 multiplied by 10, because we're going to have 50,000 over here as well. So that's mg, and it just means we've got a common factor we can take out. 50,000 over here, v squared over 4,800 times 13/5. So we've 13 is common to both sides, 50,000 is common to both sides, and 12 comes out here. If 12 comes out here, leaving 400. Okay, so we get 10 equals, 10 equals v squared over 400 multiplied by 5 is 2,000. V squared is 20,000, and v is the square root of 20,000. (141 meters per second, 0.4 meters per second. There's the speed that the plane is traveling at if it needs to bank at a radius of 4,800 meters per second. Okay, so that's question 7, and the last question we're going to look at is question 9. I will look at the harder questions in this exercise in a separate video. So question 9 is a bit of a funny one. It's a bit of an artificial problem, but it's it's instructive in some respects, so we'll have a look at it. Between the points A and B, we've got a string. Now the same string going the whole way through here, okay, is threaded on a piece of string which is 3.2 meters long. That is, the whole length of the string is 3.2 meters. B is 2.4 meters below A, that's B there, so that's 2.4 meters. The ring describes a horizontal circle at center B with angular velocity omega. Okay, so we're swinging this ring around. It's stuck between these 2 points, and we're getting circular motion. So find the radius of the circle of motion. Now that's just a geometry problem. What you have is a triangle that is 2.4. We'll call this radius x, and then this distance here is 3.2 meters, is the full length of the string, so this is 3.2 meters minus whatever the radius is. So Pythagoras tells us that x squared plus 2.4 squared equals 3.2 minus x squared, or x squared plus 2.4 squared is 5.76 equals 3.2 squared is 10.24. So that's square the first plus square the second, x squared, plus twice the product is minus 6.4 x. Okay, so moving everything to, well, I suppose we've got x squared on both sides, so subtract x squared from both sides, and then move that over. You get 5.76 minus 10.24 equals minus 6.4 x. 5.76 minus 10.24 is minus 4.48 is minus 6.4 x. X is minus, if you like, 4.48 divided by minus 6.4, and we get an answer of 0.7 is the radius, that distance there. Okay, so we can go back to our problem and mark that in. That's 0.7, and that's 2.5 then to make it up to 3.2 meters altogether. And that's, if you might be familiar with the 7, 24, 25 Pythagorean triple, it's just that triangle all divided by 10. Part 2, find omega in terms of g. So let's go and have a look at what the forces acting here are. So you got the weight of the ring, as usual. Now the tension in the string has to be the same throughout the whole string. So the tension acting inwards here and the tension acting upwards here are the same. This one is a straight inwards force, but this one needs to be resolved. Okay, so the tension acting in that direction, this angle here is the same as this angle up here. Okay, so if that's t, and this is t cos theta, and this is going to be t sine theta here, well, t sine theta opposite over, now remember that came out as 2.5, and that came out as 0.7. So it's t times 2.4 over 2.5 is your opposite over adjacent, and this is t times 0.7 over 2.5. Okay, that could be 7 over 25 and 24 over 25 if you like as well. So we've got that extra force acting inwards, which is 7/25 of t, and we've got this extra force acting upwards, which is 24/25 of t. So our forces up equal our forces down. Tells us what the only upward force is the upward component of tension here, okay, which we worked out down here is 24 over 25 t, and that equals the weight mg. Okay, our forces inwards, I should say forces up, our forces inwards are the centripetal forces. That's what's responsible for our circular motion. So our inward force here is T, tension in the string from here, plus the inward component of this, which we've worked out is 7/25 of t. That gives us a centripetal force. This question is asking about omega, so we're going to use the m omega squared r version of centripetal force. So this tells us that t is 25 mg over 24. And this tells us t, so that's 25/25 plus 7/25, that's 32 25ths of t is m omega squared, and our radius is 0.7 from the first part of the problem. Okay, so let's sub t in. 32 over 25 times 25 mg over 24 equals m omega squared times 0.7. So m's cancel. Okay. Here, it's common to both sides. Here you've got 25 top and bottom of your fraction, so that cancels. 32 over 24 is the same as 4 over 3. Okay, so you're cancelling 8s out of that. So we're left with 4g over 3 equals omega squared times 0.7. Divide through by 0.7, you get 4g over 3 by 0.7 is 2.1 equals omega squared, and then omega is the square root of that. Now I'm just going to multiply top and bottom by 10, 40g over 21, so that I've got whole numbers, and then take the square root. So the question said find omega in terms of g, and there it is. Okay, I'll look at the tougher questions in the next video. See you.